Good morning, girls. Today we're going on to the next lesson in science. We are on 4.2.4, Power, Machines, and Force. There are some formulas in this chapter that'll help us to determine what is power and what is mechanical advantage. So let's hop right into it. So power, machines, and force on page 242. Let's look at some vocabulary and objectives first. So objectives: to define power in terms of work and time, describe the benefits of machines, calculate the mechanical advantage. Vocabulary: effort force, the force needed to do the same work with a machine. A machine is a device that makes work easier by changing the size or direction, or both, of force. Mechanical advantage, a measure of how much machine increases a force applied to it. Power, the amount of work done or energy provided in a period of time. And resistance force, the force needed to do work without a machine. All right. The word power is used in many ways. It is said that a storm packs a lot of power, that someone has a lot of muscle power, that the government official is in power. In physics, however, power is the amount of work done or energy provided in a period of time. Average power can be calculated by using the formula P equals W over T. P is power, W is work, and T is the time used to do the work. The unit for power is joules per second. 1 joule per second is defined as a watt. The watt is named after James Watt, a Scottish engineer who made steam power practical to use in 1769. Electrical devices are rated for the power they can deliver. For example, a light bulb provides 6,000 joules of work in 60 seconds and has a power of 100 watts. 1 kilowatt equals 1,000 watts. Electric companies use the kilowatt hour to measure the amount of energy used. A kilowatt hour is the energy used by a device that operates at a power level of 1,000 watts for 1 hour. If you look on the side of your house, you have an electric monitor or meter, and they used to come and check those meters to see how many watts or kilowatts your house is using of electricity. Now everything's digital, and so they can do it that way. But it used to be that this meter was on the side of your house, and you could see the little ticker moving up as you used electricity, and they would use that to kind of calculate how much electricity you've been using. Some tasks, because the force of direction involved in the work requires a lot of power. A machine makes work easier by changing the size or direction, or both, of a force. For example, lifting a treasure chest straight out of a hole would be difficult than tying a rope around it and using a pulley suspended from a tree branch to lift it. The pulley, which makes the work easier, is a machine. Machines lessen the work in one of 4 ways. Pulleys change the direction of a force. Pulling down is easier than pushing up because the work is in the same direction as the force of gravity. So if you think of it, if you're lifting something straight up, that's more difficult to do than if you were pulling down on a rope that then pulls something up, because gravity pulls you down. So if you're moving in the same direction as gravity, if you're pulling down, then it's going to be easier than picking up, because when you're picking up, you're going against gravity. Gears on a bicycle reduce the size of the force that must be applied to a moving object over a distance. Levers transfer force from one place to another or increase the size of the force. A shovel, acting as a lever, transfers the force of your arm pushing down on the handle end to the blade end. Car jacks increase the size of a force. A small force on a handle of a jack translates into a large force on the body of the car, raising the car off the ground. One thing I love to do is chop firewood. I know that might be strange, but I love it. And so I've been chopping a lot of firewood lately because we have some trees that need to be split. And so an axe can be used as a lever as well, or getting it out of a log. You would use kind of a lever system. And so in order to do that, when you strike a log, you have to, you can, if it gets stuck, if it's a really hard piece of wood, it's hard to just pull it up, and you can't just yank the axe back out of the wood because of the force, the pressure on that axe from the wood. But if you were to take another hard object, or your foot or your hand, and hit the end of the axe handle, then it'll just tip right over, and then you can pick it up. So again, moving with the direction of gravity, pushing down on that handle at the other end to release the axe head out of the log is a lot easier than just trying to pull straight up on that axe head to get it out of the log. The force needed to do work within a machine is called the resistance force or load force. The force needed to do the same work with a machine is called the effort force. If a person putting 20 kilogram box into a truck lifts the box straight up from the ground and places it in the truck, the force of gravity acting on that box is 200 N. Remember, F, or force, equals mass times acceleration, and the acceleration of gravity is approximately 10 meters per second. So you would be multiplying 20 kilograms times 10 meters per second to end up with 200 N, or newtons. Therefore, the resistance force is about 200 newtons. If the person pushes the box up a ramp into the truck, the effort force is less than 200 newtons because the box is not being pulled straight up. The effort force might only be around 40 newtons. Pushing a 40 newton box is easier than lifting a 200 newton, and the ramp acts as a machine to make the work easier. Keep in mind that the 40 newton is exerted over a longer distance. The ramp, like all machines, offers a trade-off. A smaller force can be applied, but it must be applied over a longer distance. Although the work is easier, the same amount of work is done. If you think about climbing, if you've ever hiked a mountain or hiked a steep rock, if you've been to Red Rock, which I know some of you have over this time, it's the same thing. If you were to climb straight up a rock face, that's going to take a lot of your own force to push yourself up that steep incline. Or if you were to walk a path that kind of jackknives up the side and switchbacks up that mountain, it's going to take a lot less energy to get up that same mountainside. It's going to take you longer because you are now going on a path that is longer to get to the top, but you're not moving at such a steep incline. And so it's not exerting as much energy from your muscles in order to make that ascend. A machine can increase the force that is applied to it. By using a machine, a load of 200 newtons could ideally be moved up a ramp with an effort of 40 newtons. A measure of how much machine increases a force applied to it is called mechanical advantage, or MA. The mechanical advantage can be calculated by dividing the resistance force by the effort force. So MA equals resistance force over effort force. In this case, the mechanical advantage of using the ramp is 5. 200 newtons divided by 40 newtons. So the amount of newtons it would take you to push it on your own versus the amount of newtons it would take you to do it with a machine. And that difference, quotient is 5. What does that mean? It means that the machine magnifies the effort by a factor of 5. But this does not take into account the friction that is acting on the box as it pushes up the ramp. The calculated mechanical advantage that does not take in friction to account is called the ideal mechanical advantage, meaning that's what you're hoping is going to be the difference. To truly know the mechanical advantage, the resistance of friction needs to be subtracted. Friction always works in the opposite force. So they have a picture there. You have resistance force would be picking it straight up. Effort force would be pushing it up a ramp. And that ramp is being used as a simple machine. Try this. Bulb swap. Take an inventory of the incandescent bulbs in your school or your house. Record the wattage for each. Research fluorescent or LED replacements for those light bulbs and record what the new wattage would be if all the incandescent bulbs were replaced. Calculate and compare 1 hour of power usage of the old bulbs to one of the new bulbs. Could you save energy by swapping out bulbs? I know some of you have had Mass Save come to your house and do an electrical audit. We did as well. And one of the things they do is they give you new LED light bulbs instead of incandescent light bulbs because they do use a lot less energy and they run more efficiently and they run for longer periods of time. And so check your house, see what kind of bulbs you have, and do a little research. What is the difference between incandescent and LED light bulbs, and why is it worth investing in? All right, Bible connection. God's power. God chose Gideon to lead the Israelites against the Midianites, Judges 6-8. But Gideon did not feel powerful enough to do what God asked. God consistently reassured Gideon that he had a plan that included Gideon leading the attack. The only work God required of Gideon was his 300 men, and his 300 men was to break vases, blow trumpets, and yell. The actual defeat came through God's power as he set the Midianites against themselves and sent them running into the night. When God calls his people into action, he provides the power to do the work. In the For Your Information chart there on that page in yellow, you have kind of a cheat sheet per se that can show you what generally different electronics use for wattage. And so you have a cell phone charger is about 10 watts, a Blu-ray or DVD player is 15 watts, a tablet is 10 to 20 watts, a 32-inch LED LCD TV is about 50 watts per hour. Remember, this is per watts per second. A laptop computer is 20 to 75 watts. A video game console is 40 to 140 watts. A 42-inch plasma TV is 240 watts of energy. Refrigerators are 500 to 750 watts. Washing machines are 500 to 1,000 watts. Coffee makers, 600 to 1,200 watts. That's amazing that a coffee machine uses more energy than a washing machine and a refrigerator. A vacuum cleaner is 300 to 1,500 watts. A toaster is 800 to 1,500 watts. A hair dryer is 1,000 to 1,875 watts. And a microwave is 1,000 to 200 watts. So if you think of the electronics you use in your house, what things generate more electricity than others, I always knew a hairdryer was way up there. But even some of the smallest appliances that you think, oh, I'm only using it for a minute and I'm not, and it's so small, they take a lot of energy, especially if it's an electronic used to heat something up or to cook something. I know in the summertime you can ask your parents, like, when is our electric bill the most expensive? And it depends on what devices you're using. And so in the spring, if you have like a dehumidifier that runs in your basement, then your wattage that your house is using is going to go way up because dehumidifiers use a lot of electricity. If you run air conditioners in the summer, those use a lot of wattage, and that's extra electricity that you're using over those couple months of the summer. And so your parents probably see the electric bill go straight up. But on the other hand, if your house is run off of electric heat, then you're using less heat in the summer, less baseboard heat, and so your cost of heating your house is going to go down, but now you're paying for the cost of cooling your house. Or maybe your parents use the stove less in the summer because you're grilling or because you're doing picnics and not cooking as much. Or maybe you don't use your hairdryer as much because it's really hot out and your hair can just dry outside. But it ebbs and flows, the amount of electricity that we use and the amount of wattage. And so that's something that you can look at on your electric bill, on your home's electric bill, is it'll tell you how many kilowatts you used over a period of time. And you can compare all of those bills to see what it looks like over a year. And if you have a really high kilowattage that you use, go around your house and think of ways that you could maybe cut back on using electricity. That'll cut back on your costs. Sometimes things as simple as just unplugging electronics when you're not using them, unplugging your toaster, unplugging your microwave, unplugging anything that just stays plugged in, that'll save you money because they actually do use wattage even though it's not creating heat or, shining light at that moment. Being plugged in does generate a small amount of wattage that you're using. And so just by unplugging things when you're not using them, you can save money and wattage that is being used. All right, laws and principles down at the bottom. The formula for power, you have power is the amount of work done or energy used in a given amount of time. The unit for power is called a watt, which is defined as the number of joules in 1 second. So P equals W over T, wattage over time. So here's an example. If a drill runs for 10 seconds and uses 500 joules, the amount of power is 500 joules, so the wattage, over 10 seconds, which is 50 watts per second. How many watts would the drill need if it used 1,000 joules in 10 seconds? Joules per second would equal 100 watts. What if you used a 200 watt drill for 10 seconds? How many joules of energy would it need? 200 watts times 10 seconds would be 200 joules. And if you needed to figure it out for longer amounts of time, then you would just multiply it by a different amount of seconds, a different time. Okay, questions for today. You do not have a lab today, so you're just answering these questions. So first, what is power? So define what that is. Number 2, what is the power of a machine that does 3,000 joules of work in 60 seconds? Okay, so again, you can look at that equation down at the bottom, P equals W over T. So you're doing wattage, which would be 3,000 joules, over time, which would be 60 seconds. So you're dividing those. 3, compare resistance and effort force. So in definition, what is the difference between resistance force and effort force? How do machines make work easier? So just give some examples of why do we use machines and how does that help us and why is it beneficial? And 5, what is the mechanical advantage of a machine that uses an effort of 25 newtons to lift a 125 newton load? And what does that mean? So if you go back to look at the formula for mechanical advantage, you have the resistance force divided by the effort force, okay? And so the resistance force would be what it would take for you to do it without using a machine, divided by what it would take you to do it with a machine, and you're dividing those together, okay? If you have any questions on that, just let me know. Do your best on it. And next time for science, we're going to go on to the next section, which is efficiency and friction. So we're going to continue talking about simple machines.